Math 1343, Week 3, Video 2. First example of estimating one population mean. Let's take a look at an example and see just how easy it is to construct a confidence interval for one population mean. Study of n equals 60 domestic cats that hunt outdoors showed that the mean number of kills per week for these cats was 3.1 with a standard deviation of 1.46. Find and interpret a 95% confidence interval for the mean number of kills per week by domestic cats that hunt outdoors. You realize I have a typo here? It's going to bother me. There we go. All right, before we jump into this, I do want to point out that in the previous week's videos over estimating one population mean, estimating the difference in two population means, we didn't actually interpret the results using a complete sentence. I'll be demonstrating that from this point forward when we build confidence intervals, with the understanding that such interpretation also applies to the types of confidence intervals in the previous week's videos. But let's dissect this problem and figure out how to estimate the mean number of kills per week for all domestic cats that hunt outdoors. And honestly, I think the word all would be appropriate. The nature of inferential statistics is to say something about a population based on a sample, so it's nice to have a word in there that implies the population, such as the word all. Okay, so how do we do this? Well, I know a lot of people fear math when there are word problems, and needless to say, statistics is more word problems than not. But there's a trick to handling most word problems. The trick is to make them not word problems. How do you do this? Well, you go through the problem and you extract all the information that you're given, and then you determine the information you want to find, and then you bridge the gap between what you know and what you want to know. The very first information that we're given is n equals 60. And although it's explicitly stated there, sometimes it won't say n equals. Sometimes it will just say a study of 60. But that is a population size. So let's start by listing everything that we're given. Given us a sample size of 60, not a population size. But let's see what else we're given. A study of 60 domestic cats showed that the mean number of kills per week was 3.1. All right, the mean was 3.1. And this is from a sample, even though it doesn't explicitly say the word sample. You can infer that it's a sample because there are only 60 domestic cats. To claim that it was a population would mean that you're saying there are only 60 domestic cats in the world. It's clearly not true. All right, so our mean was 3.1, and since it's from a sample, the variable is x bar. And right after that, we're given a standard deviation of 1.46. Because we're still talking about the sample, that's lowercase s. We are given one more number, 95% confidence level. We'll just say CL for confidence level, 95%. And we are asked to find basically a confidence interval for mu. Now, you don't have to literally write all this down. I would write down the givens. You don't have to rewrite the question or what your goal is. In this case, it's to find a confidence interval for mu. But this is how you attack word problems in general. You write down everything they give you, and then you write down what they want you to find, and then you find the gap, you bridge the gap between what you know and what you want to know. Now, of course, we're going to be doing the same 4 steps that were enumerated in the previous video, so let's get right to it. Number 1, find t. This is just like finding z, where we sketch the bell curve, and confidence level represents middle area of the bell curve. Now, to find the t, we need to know 2 things. We need to know the left area and the degrees of freedom. In fact, it might be a good idea to pull up a T-chart real quick. All right, here's the T-chart that I opened up from Canvas. If you have trouble locating it, let me know. But I showed you where to find it in the previous video. Remember, in the T-chart, we need the area of the right tail, and we need degrees of freedom. I might have accidentally said left tail. Long pause while I was opening this. But let's go back to the problem that we're working on. All right, so, well, the left tail and the right tail will have the same area. Remember that the total area under the curve is 100%. Since 95% is in the middle, that means that these two tails together will total 5%. So if we cut that in half, we get 2.5%. For our degrees of freedom, just the sample size minus 1. But our sample size is 60, so n minus 1 is 59. Going to our T-chart, we need 2.5% on the right tail and 59 degrees of freedom. 2.5% on the right tail is the third column. Go to the second page. 59 degrees of freedom. Our T is 2.001. 2.001. Write that here. 0.010. And of course the other one is negative, but we only really need one of them. Let's draw a line separating step 1 from step 2. And now let's go to step 2. Step 2 is to find the standard error. And the formula for standard error here is much easier than it was when we were estimating one population portion. It's just standard deviation over the square root of the sample size. Our standard deviation was 1.46. Our sample size was 60, so square root of 60 in the denominator. And most of the time this will come out to be a nasty decimal. So we're going to stick with the same protocol as before, which is to round to 4 decimal places. I highly recommend getting out your calculator right now and seeing if you get the same value that I do. My standard error, I got 0.1885. It was actually 1884, but the next digit was 8, so the 4 rounded up to a 5. Let me do it again just to make sure. Even the best of us will make casual mistakes if we're not careful. I did it again and got the same answer again, so I'm pretty sure it's correct. All right, let's do step 3. Step 3 is to calculate the margin of error, but this is the easy step regardless of the type of confidence interval you're doing. Because to find the margin of error, you always just multiply the answer to the first question, T, times the answer to the second one, error. Our T was 2.0010. Our standard error is 0.1885. And I'm going to use the same rounding protocol as before. I'm going to round my answer to 4 decimal places. And to 4 decimal places, I got 0.3772. Actually a 1, but the next digit was 8, so I rounded up. All right, so that part was pretty easy. The last part, I think I can fit all this on one page. No, we'll just go to the next page. The last part, we're going to find our interval. And remember, your interval is always the sample version of what you're estimating. Since we're estimating population mean, our sample version is sample mean x bar, plus or minus your margin of error. Well, this is pretty straightforward. Our x bar is 3.1. Or minus our margin of error is 0.3772. And so we'll write our answer in the form from the lower number to the upper number. To get the lower number, we're just going to subtract 3.1 minus 0.3772, that will give us 2.7228. And then the upper value, the upper limit, if you will, is the answer to the addition problem, 3.1 plus 0.3772, which is 3.472. So in terms of calculations, the problem is over. We have our confidence interval for mu. We state with 95% confidence that the population mean is between 2.7228 and 3.4772. But how do we interpret that? In other words, when you're doing a problem and you're being asked to interpret confidence interval, how do you do that? Well, it's actually very straightforward, and I'll show you on the next page. Since our confidence interval was from 2.7228 to 3.4772, we can interpret that in the context of the problem. Now, as I'm typing this interpretation, I'm going to start by typing the generic way to interpret a confidence interval and then change it to just to interpret this specific situation. The interpretation goes something like this. We state with, and then you state your confidence level, or confidence. State with whatever confidence that, then you describe what you estimated. I can type is from, and then you write your interval. So it's actually a real easy something to do. I'm going to copy and paste this. I want to leave the general interpretation up there, and it's the word describe. But then I'm going to type it again, but this time I'll replace the generalities with specifics. For example, in this confidence interval, the confidence level was 95%. So we start by saying we state with 95% confidence that. Now, as far as describe what you estimated, let's go back to the word problem for a second. What did we estimate here? One side of here. We estimated the mean number of kills per week by all domestic cats that went outdoors. That's what we were estimating. So let's copy this and let's go put it . Of course, it takes more time as you're writing it by hand. We state with 95% confidence that the mean number of kills per week by all domestic cats that hunt outdoors is from, and then you insert your interval. Let's insert our interval here. And we have our interpretation specific to this problem. State with 95% confidence that the mean number of kills per week by all domestic cats that hunt outdoors is from 2.7228 to 3.4772. And if you wanted to make it even more specific, you could put units of measurements on your numbers. In this case, it's kills per week. So we state with 95% confidence that the mean number of kills per week by all domestic cats that hunt outdoors is from 2.7228 kills per week, 3.4772 kills per week. Again, I can't stress enough that the interpretation of a confidence interval is actually very predictable. All you have to do is say a statement like this, replace the confidence level with the specific confidence level, describe what you estimated, in other words, what your population variable was measuring, and then, of course, your interval